Okay, cool. So I'd like to get started. There's a lot of stuff to talk about today, and this is a kind of important topic. It's going to form the foundations of a lot of the stuff we're going to do next. So we'll get right into it. And I'm going to be talking about language modeling and sequential prediction problems more generally. And before we actually get into modeling techniques, I'd like to talk about different types of sequential modeling problems. And there's a variety of types of prediction problems. And at the very least, if you've taken a machine learning course before, you'll definitely have heard of binary classification, which is a decision between two choices, like negative and positive. And multi-class classification, which is a choice between multiple choices, like very good, good, neutral, bad, very bad. In addition to this, there's something that's really, really important in natural language processing, also some other realms as well, called structured prediction. And structured prediction is a type of multi-class classification because you have many, many different classes, but the number of classes is so large that you can't enumerate them all. And so because of that, you need to somehow take advantage of the structure of the course, of the prediction problem. So to give a couple examples, this is part of speech tagging. And part of speech tagging is the input is a sentence, and the output is a part of speech for each word in the sentence. Then for translation, the input is a sentence, and the output is another sentence. So first, a quiz. Let's say we have n part of speech tags in our vocabulary. How large is the label space for, or let's say we have v part of speech tags in the vocabulary. How large is the label space for this task? V to the power of n, where n is the length of the sentence. So yeah, very good, because we have one different one each time. So importantly, the label space for this problem is not v. It's not just the number part of speech tags. It's actually a combinatorial number based on the output length. What about this one, where we have input sentence and output sentence? So v is the size of the vocabulary. Any ideas?
V is the size of the input vocabulary?
V is the size of the output vocabulary.
V to the power?
V to the power of n, where n is what?
It can be infinite.
It can be infinite, yeah. You could output for a very long time. Of course, for translation, you probably wouldn't want to do that. You'd want it to be approximately the same length. But if we're talking about ChatGPT and asking it, what is the meaning of life? It could go on for a while. It might write a book, right? So, it's a very large label space. Other types of prediction, we have unconditioned versus conditioned prediction. So unconditioned prediction, we're predicting the probability of a single variable, x, and it's not necessarily conditioned on anything. And this is called a number of other things. It's also called density estimation or other things like this, but you're basically just trying to predict the probability of data. Conditioned prediction, you want to predict the probability of an output variable given an input. And so you're always given, or you are given an input x, and you want to calculate the probability of the output given this input. So if we think of types of unconditioned prediction, so actually, sorry, I'll give some concrete examples of this. This is something like language modeling. So where you want to predict the probability of like a document or lots of different documents or something like this. This is everything else. This is like basically everything else in NLP. So the only time you'll actually want to do unconditioned prediction is where you're given a whole bunch of text and you want to calculate the probability of it. And most other tasks, we give some sort of input, be it a prompt or an image or something else, and try to predict the output based on that. So we have different ways that we can make unconditioned predictions. And remember, because we're now doing structured prediction, we're not necessarily able to create this huge multi-class classifier where we predict the probability of every sentence in the world. So what we do instead is we break down the problem and we predict one thing at a time. And the most common way we do this, this is the way that most large language models do it nowadays, is something called left to right prediction. Some people call this autoregressive prediction, which is kind of a broader concept. And the way this works is, let's say we have a sentence X or a sequence X. We want to predict the probability of X. The way we do this is we take the product of the probability of the next token given all of the previous tokens. And so if we do this, there's two notable things about this. The first thing is, this is just a rule of, if we ignore the fact that we need to train a model to do this, this is just a rule of probability. It's the probability, it's the chain rule. And basically it says that this prediction here is exactly, or sorry, not prediction. This probabilistic formula is exact. So there's no approximation that goes into this. And so the good news is a model that looks like this can be arbitrarily accurate. Like GPT-4 could model the true probability of language if it was estimated correctly with a good learning algorithm and a good model. Some examples of how we actually do this modeling are RNNs or transformer-based language models. And we'll talk about both of those in the next in this class and next class. What I have up here is a graphical depiction of this. And basically what this is saying is each row X is a prediction that we make. Each column is the token position in the sequence. And the red is the thing that we're predicting. So we're predicting the first token and then the second token and then the third token. The black part is the context that we use. And the white part is the context that we don't use. So when we predict the first token, we're conditioning on nothing. When we predict the second token, we're conditioning on the first token, but not any of the following tokens, et cetera, et cetera. Yes?
What is the etymology of the term autoregressive? Why is it called?
Autoregressive. So the reason why it's called autoregressive is because I believe this comes from regression models originally, not classification style models. So like, I assume that people have heard of regression and classification. Regression is when you predict a continuous variable. Classification is when you predict a discrete variable. But basically, autoregressive models were models that predict future continuous values based on the previous values that they got. And the reason why it's auto is because you would generate the output and then generate the next output based on the predicted output. So the auto comes from the fact that you're using previous generations. Yeah. Cool. Any other questions? One thing I should note is autoregressive is a broader term than left to right, like I mentioned before. You could have a right to left autoregressive model also, where you predict the last token first. The reason why we don't do that is basically because people speak from like past to future, right? So there's kind of a natural order to language. Notice I didn't say people write from left to right, because there are people who write from right to left also, like people who speak Arabic or Hebrew or other languages that are written right to left, but everybody speaks from past to future, right? So because of that, there's a natural order. Okay, so the next one is left to right Markov chain. And the basic idea behind this is, instead of predicting based on all of the previous context, we predict on a limited window of the previous context. And there's a couple reasons why we would do this. Does anyone have an idea why we might want to limit the amount of history that we're taking a look at? Yeah.
Would it be able to do like infinite sequence length vectors? We can limit ourselves by.
Yeah, so we could handle an infinite sequence length. So if we use the first one on an infinite sequence length, what happens? Yeah, we run out of memory, basically. So the problem is, if we had this be, you know, 1 billion tokens, we would try to fit all of it in memory and it would crash. Instead, if we limit it, then we don't. And so even RNNs in transformer models, in their actual implementation, they are limited in context. So they'll have like an 8,000 context length or a 128,000 context length or something like this. There's also models that are kind of more explicitly limited in the amount of context they handle, like Ngram LMs and feed-forward LMs, and I'll talk about those in a second. Another thing we can do is independent prediction. So basically, we predict each token individually and then calculate the probability. This also is a language model. It's called a unigram language model. It's not a very good language model for kind of obvious reasons, like, you know, words don't just happen randomly, they happen in context, so we need to keep track of context, but that's another method. Now, a final one is bidirectional prediction, and this is where you predict the probability of a token given both the left and right sides. This is used in things called masked language models. However, there's a problem with these. Does anyone know what the problem is? Any ideas?
Takes up a lot of memory.
Takes up a lot of memory. It doesn't take up enough more memory than the top one for that to be the main problem. Any other ideas? Yeah, so it's similar, saying similar things. It's tough to generate new sentences. And the reason why is, let's say you want to generate the first word in the sentence, but you need to condition on the second word. Which one do you generate first? That's the problem, right? So you're not actually able to generate from these models. And another problem is they're not actually probabilistic models. Or you need to work really hard to turn them into something that looks like a probabilistic model. In contrast to all of the ones above, these are all reasonable probabilistic models where you can calculate the probability of a sentence given the previous ones. So, however, these are very good. They're good for things like representation learning, like learning representations of words. And so they are still used, but they're not actual. Despite the name masked language models, they're not really like language models that can calculate the probability of sentence or something. Yeah, so from the perspective of causality, how do these work? They don't really. Like, so you can't generate a sentence from them precisely because there's no causal model of like the next word given the previous words. So yeah, we're going to explain a bit more about that later in a later class. But basically, the way it works is you mask out the input and predict this token, and then you can use that to learn representations of that token. Yeah. Cool. And these are represented by things like BERT or you know, Roberta or other things like that if you've heard about those. Cool. So now types of condition prediction. This is an example of a condition prediction. It's very, very similar to how we predict, you know, before, but now you don't necessarily even need to predict the things in the source or the input, and you can just predict the output. So you start out by predicting the first word in the output. This can be transformer-based sequence models. They can be encoder-decoder models. It can also just be a language model where you don't predict the probability of the prompt and you predict the probability of the continuation only. There's also methods for non-autoregressive condition prediction. We're not going to talk about them a whole lot, but basically the way these work is they predict each output kind of independently from all of the other outputs. One way you can do this is for sequence labeling. So for something like predicting the part of speech tag of an output, you can just calculate representations for everything in the input and then predict all of the part of speech tags independently. So these are the basic ideas. The basic modeling paradigm is very similar to what we talked about last time, extracting features and predict. So given an input, we extract features and predict labels. And in text classification, the way we did this is we predicted a single feature vector. For sequence labeling, we basically calculate a feature vector for each element in the sequence or each element we want to predict and make a prediction here. So if we were just predicting the part of speech tags, what we would do is we would predict a vector for each of the words we wanted to predict a tag for and generate an output. And then for language modeling, it also looks similar to this. And I'll talk about language modeling in particular next. Cool. Any questions so far? All set? Okay, great. So another distinction I'd like to make is generative versus discriminative models. And discriminative model is a model that calculates the probability of a latent trait given the data. And so this will always have a conditional model like this, where we have the input X and we want to predict the output Y. A generative model is one that generally calculates the probability of the input data itself, or one that calculates some sort of joint probability like this. And language models tend to fall in the latter half. Usually we pre-train a language model on just data. So we pre-train it using this kind of standalone generative objective. And then we may do fine-tuning. And when we do fine-tuning, we might calculate this sort of joint probability or conditional probability. And we're going to talk about instruction tuning later, where we talk about methods to do this. So a language model basically is calculating the probability of a sequence. This could be like a sentence or a document or anything else we want it to be. And it's a generative model that calculates the probability of language. If we look at all the things that we can do with LLMs, there's many, many things we could do with LLMs, right? We look at what ChatGPT can do, or you know, the whatever API-based model, Llama. It's a bunch of different things, but basically they all boil down to two things, essentially. There might be a couple other things that you can do with LLMs, but almost all of the things we do with them boils down to one of two. So the first one is scoring sentences. And the way this works is basically you get a sentence and you calculate its probability. And if it's a good sentence or a likely sentence, according to the model, it gets a high probability. If it's an unlikely sentence, we get a low probability. And this is the way we train models. So what we do is we calculate the probability of some, or this is the most common way to train models, or the first way we start out by training models. And the way we do this is we calculate the probability of data that we like in some way. We think it's like natural language data, and we try to raise the probability by adjusting the parameters through backpropagation. The second thing we do is generate sentences of some variety. So that might be sampling sentences according to the probability distribution or finding the highest scoring sentence or something like this. But basically, it will be one of these two things. So if we look at how we can apply these two operations, we can do things like answer questions. And the way we can answer questions is twofold. Let's say we have a couple multiple choice answers. The way we could answer the multiple choice question is we could score all, 4 of the answers or all 10 of the answers and find out which one gives us the highest probability. Another way we could do it is we could generate a continuation of a question prompt, and that would allow us to answer questions. And in reality, both of these are used in practice. For evaluation, it's very common to score multiple choice answers. In most practical systems, we tend to generate answers, but there is scoring in multiple choice used as well. Classifying text. One thing that we can do for text classification is scoring the text conditioned on a label. So if I say, or there's a couple ways we could do this. It's like, we could have, I love this movie. And so this would be a movie review, and then we say score. This would be part of the prompt, and we would feed in a prompt. And then we would calculate the probability of 5 stars, 4 stars, 3 stars, 2 stars, 1 star. And so this would be a way we could use scoring to classify the text. Another way we could do it is score 5 stars. And then score the probability of I love this movie. And so here, based on the probability of the input, based on the input prompt, you calculate the probability of 5 stars or 4 stars or 3 stars or something. The other way you can do it is you can prompt the model based on how good the movie review is and then generate and calculate the generative probability here. And these are called discriminative classifiers versus generative classifiers. Yeah, so you can do this. And then finally, you can also just generate the label. You could sample a label from the language.
It's something you do with instruction to not like a very pre-training output.
Oh, this is an inference time. I'm not talking about training at all. You might not even have to train the model to do this. Cool. Any other questions about this? Okay, sounds good. Oh yeah.
For something like the 5 stars and all, are there ways to enforce that the generated value be either 1 star, 2 star, 3 star, or so on to 5 stars?
Yep. Yeah, that's a great question. So the question was, is there a way to enforce that the output is of a particular nature? And the answer is there's 2 ways to do this. One way to do this is to say, please output in this format. And the language model, if it's an appropriately, instruction-tuned language model, will follow your directions. A more direct way of doing it is to enact some constraints at generation time. And I'm going to talk about those a little bit, but basically the easy way you can do this is you create something called a trie that maybe a lot of people know from like a data structures class or something like this. And it's basically a tree like this. And what you do is when you're generating the first token, you say it can only be something that's in this first level here. And so you mask out and give 0 probability to all the other tokens, and then you continue on. So there are libraries that implement this sort of thing and stuff like that, but there are ways you can add constraints to models too. Yeah. Great. Cool. Another thing is correcting grammar. So the way you can do this is you could score each word in the output and replace the low scoring ones in some way. So this would be using the scoring capability, or you could generate a paraphrase of the output and say, please, turn this into a grammatical sentence. So basically what I wanted to say is like for any problem that you're tackling, there's usually multiple ways to think about how to handle it. The easy way is often through generation of some variety. But sometimes it's more accurate to use scoring in some way, or it gives you more fine-grained control about how you could visualize outputs or things like that. Cool. So I'm going to jump into autoregressive language models. Autoregressive language models, as I mentioned before, we predict the next token based on the context. And usually, 90, 98, 99% of the time, this is going to be left to right. And so then the big problem becomes, how do we predict the next token? And the first one I want to talk about is unigram language models. And these are not great language models, but they're also very, very easy to implement. So, they give a good intuition about what we need to implement and some of the difficulties. So the simplest language model is a count-based unigram model. And what we do is we give a independence assumption and say, we're going to predict each of the words or each of the tokens in the output independently. And we can actually directly estimate this model by counting up all of the occurrences of a particular word in the training corpus and dividing by all of the, sorry, I'm using word and token interchangeably, but if I say word, I mean token. So please replace it in your head. So count up all of the tokens in the training corpus and divide it, all of the tokens of a particular type in the training corpus and divide it. So basically, if you have, 500,000 occurrences of the word the in your training corpus of 10 million tokens, it would get a probability of 5%, which is about right for the word the. Okay, so this is the one time when I do mean words. So if we have unknown words, if the token or word doesn't occur in the training data, its probability becomes 0 because the numerator here becomes 0. The problem with things becoming 0 is that, remember, we're multiplying these probabilities together. So if anywhere becomes 0, then everything becomes 0. So there's a couple ways to handle this. The first one is to segment down to characters or subwords to make sure that all of the tokens are in the vocabulary. This is the most common way to do this now. You can also do something like create an unknown word model. So this is like a hierarchical model where you have a token level model that you use normally. And then when you get an unknown word, you calculate the probability of the unknown word. And this is not super common, but it gives you a good intuition about smoothing, which I'm going to be talking about next. And basically what smoothing does is it combines together the probabilities of two models. And so here, let's say you have this maximum likelihood estimation model. And so this is a good model in general, because you estimated it by counting up your like very large corpus and dividing all of the probabilities. But every once in a while, it gives a probability of 0. And so, for example, if we set this lambda unc to 0.05, 95% of the time, our model would try to generate something from the actual vocabulary that we predicted. But 5% of the time, it would try to generate something from this unknown word model. And the good news about this is if this unknown word model will give every word or every token at least some probability, then we're guaranteed to not ever have not ever have a probability of 0. We might have some words that have a very, very low probability, but they'll never have 0 probability. So we'll always have a well-formed probability of generating the output. Yeah.
In this case, the model will not be able to differentiate between different unknown words, right? It will treat them the same.
So will the model not be able to differentiate between various unknown words? Will it treat them the same? That's one way of doing it. The unknown word model, you could create it in as sophisticated a way as you wanted. So you could create an unknown word model that, for example, looks at the spelling of the word, and you estimate that with all the rigor that you would estimate your normal model. In reality, that's too much work, and nobody actually does that. But like if you wanted to really create the best possible model of all the words in the universe, that would be a good way to do it. So, but anyway, this is not super important because normally we take the first thing here. But what is important is knowing that you can combine together two models, like a stronger model that gives 0 probability some of the time, or a stronger model that's weak in some subset of the cases, and a weaker model that's kind of strong in all cases, or it can give non-zero probability in all cases. So, one thing to note here is there's a restriction that this must be between 0 and 1. And the reason why it must be between 0 and 1 is if we have two probability distributions and we interpolate them with something between 0 and 1 and adds to 1, we'll get a well-formed probability distribution. And all of the smoothing methods that I'm going to talk about later also make this assumption. So this could be like 0.05 and 0.95. But it couldn't be like minus 0.2 and plus 1.2 or something like that. Cool. Okay, another basic thing about language models. In language models, we very often talk about log likelihoods or log probabilities. And so I've been talking about multiplying different probabilities together, but very often we will be adding log probabilities together. Does somebody know why we do this? Any ideas? Yeah. Yeah, so the numbers are smaller for numerical stability. And basically the issue is if you look at floats, if you look at the way that floating point numbers are expressed on computers, this is a 16-bit floating point number, and it has a sign which tells you whether it's positive or negative. It has 5 bits to express the exponent, and then this is all the rest corresponding to the fraction. So basically what this says is you have 5 bits to express how big the exponential part of the number can be. And if this gets very small or very large, basically the number becomes 0 or the number becomes infinity according to the computer. And so if we have a very small number, it'll just disappear and become 0. This is a big problem because, as I said, if the number becomes 0, you start getting not a number outputs or things like this. I kind of intentionally opened this Wikipedia page because bfloat 16 is like a new version of floating points that is better tailored to machine learning. And this basically uses more space on the exponent, so you can get like larger and smaller values with respect to kind of the overall scale at the cost of reducing the amount of precision you have on the actual values. So this is used pretty widely in language model training nowadays. But anyway, so yeah, that's the reason why we do it in log space. And so if we have you know, a number that's like 10 to the minus 500, that will just be minus 500 or close to minus 500 in log space. Or in log 0 space. And if it's a natural log, it would be minus 500 times E. So, so yeah, now we have this log P, we can express them as parameters, theta for this. And next, I'd like to go to higher order language models. So like, as I mentioned, unigram models are not very good models of language because they don't consider word order at all. And higher order n-gram models are basically models that use more, that don't make the complete independence assumption and instead consider some of the previous words. So this is an example of calculating the probability of, this is an example. And so we're calculating actually calculating the probability of example given this is n. And the way we do this is, does anyone know what type of model this is? Anybody study n-gram language models before and know the name of one that has 4 words? It's called a 4-gram. It's not very interesting. But we call them unigrams, bigrams, trigrams, and 4-grams because they gave up on Latin or Greek or whatever after 3. So basically, this is how you calculate the probability using maximum likelihood estimation. And the problem with this is, I mentioned unknown words being a problem for unigram models, but for a 4-gram model, now unknown 4-word sequences become a problem. And there's lots of unknown 4-word sequences, of course. So it becomes even more important to smooth these together. And the way that n-gram models worked on this is basically what they would do is they would have the maximum likelihood estimate of the 4-gram, and then they would smooth it together with the probability of the 3-gram to get the 4-gram probability. And so the of the trigram. The probability of the trigram model is the maximum likelihood estimate of the trigram smoothed together with the probability of the bigram. So it's kind of recursive and goes all the way down maybe to your unknown word model, which means that you're guaranteed to kind of never have unknown probability there. There's lots of smoothing methods that people used in the past. These are not really important, so I'm going to go through them really quickly. But they are kind of useful if you want to combine together two probabilities in a somewhat intelligent way. So the first way to do it is just kind of this smoothing where you smooth together according to a fixed coefficient every time. Another way that they did it is they had an additive factor, which is this alpha here. And you would add the probability of the lower order probability. And so because you have this alpha, at the very beginning, you if like alpha was equal to 1, you would start out with let me arbitrarily pick the and let's say your lower order probability of these is 0.6 and 0.4. So if you've never seen the bigram hit blank, at the very beginning, you would start out with 0.6 and 0.4 for the and If in your corpus you saw hit once, then that would give you 0.6. And let's see, that would give you 0.4, 1 plus 0.4 divided by 1 plus 1. So now the probability of hit would go up to 0.7. And the probability of hit the would go down to 0.3. So basically what this means is the larger you make alpha, like let's say we made alpha 100. So, or let's say we made alpha 99. If we made alpha 99, the probability of hit would remain very, very close to 0.4. So the larger you make alpha, the harder it is to push for evidence to change the probability that you had from the lower models. So basically, by adjusting alpha, you can either make your model very conservative and stick very closely to what the lower order probability distribution is, or you can make your model very aggressive in updating it. So if you made it like 0.1, if you get a single example in your corpus, then it would change it very rapidly. And so there's a bunch of other methods like discounting, connaissances. I have a lot of material that I want to cover today, so maybe I'll just kind of skip over them. But we've talked about n-gram models. There's a bunch of problems with n-gram models. And the first one is they can't share strength among similar words. So we talked about this last time. If we're just using kind of counts, it makes it very hard to say she bought a car, she bought a bicycle. They can't condition on context with intervening words. So there was something called skipgram language models that handled this. They can't handle long distance dependencies. And so if they're beyond the n-gram context, it makes it difficult for the model to essentially handle these because the context length is limited. And so when I first started out doing natural language processing, we were using n-gram language models. And there's a really nice paper called a bit of progress on language modeling, where basically this one researcher tried all of the methods that were devised to create these n-gram language models and to fix all the problems with these n-gram language models. So it's not like people didn't realize there were problems with these and try to fix them. But basically his conclusion from this 60-page paper or 70-page paper was, this is too hard, I give up. So, like you can read maybe not the whole paper, but like the conclusion section. It's kind of interesting. It's a bit of progress in language modeling by Joshua Goodman. And so because of this, there was not a lot of progress in this paradigm because people were trying really hard, but it was just too hard to do this. So neural language models are the way to go, and I'm going to cover them next. But N-gram language models do have advantages. They're extremely fast to estimate and apply. And so compared to a neural language model, you can run these over the entire internet and like actually run them on a decent amount of hardware in a decent amount of time. So if you want to calculate like a language model-based text classifier, it is possible that you could create an N-gram language model that would actually allow you to do that. Another interesting thing is neural language models actually can be worse at low frequency phenomena. So things like, very rare entities, you can estimate an N-gram language model on the entire internet, and it actually will remember everything it learned because it's a model that you just get by counting. So there are actually places where N-gram language models can beat neural language models. And if you ever get to the point where you want to use something like that, you can use this software called KNLM, which is very fast. It was also created by somebody at CMU. So. Cool. Okay, so next step, I want to get into LM evaluation. Are there any questions on the way there? I realize I went over this kind of quickly, but okay, sounds good. So I'm going to jump into LM evaluation. Here, I'm going to talk about very, very simple methods of LM evaluation, not the very, complex things that we do nowadays. This is to evaluate a language model on its ability to model text, not on its ability to answer questions or translate or any of those other things. So the most standard way of evaluating language model performance is something called likelihood. Likelihood is like probability. Does anyone know what the canonical difference between likelihood and probability is? Okay. The canonical difference between likelihood and probability is likelihood is when you use a model to calculate the probability of data that you know is kind of ground truth, especially training data. And it technically, although a lot of people mix the terminology here, technically the likelihood is the likelihood of the parameters given the data, or the likelihood of the parameters with respect to certain data. It's not the likelihood of the data, but people mix this up fairly frequently. But basically likelihood, we mostly use it at training time because we're calculating the likelihood of our training data. Yeah.
So probability is subjective. Are you saying likelihood because it's subjective?
So the question is probability is subjective and likelihood is likelihood objective. I would say that likelihood is used in a very particular context, usually in the context of training. If you want to find the answer here you're predicting an answer, you would say you want to find the answer with the highest probability, not the highest likelihood normally. But it's not super, this is a technicality. A lot of people use it differently, but that's the technical difference between them. So a first way we can evaluate a language model is we have some ground truth data that was hopefully not included in the language model's training data, although who knows with GPT-4. And we calculate the likelihood of this. So if you're training a language model, you'll have some held out data that you want to model and you'll calculate its probability. The problem with likelihood just over a big corpus is if you switch your corpus to a different corpus, suddenly one corpus might be twice as large as the other with respect to the number of tokens in it. And so another thing that you can do is you can normalize the log likelihood in a corpus by the number of tokens in the corpus. And the reason why this is good is now, let's say you have your big news corpus with 10,000 tokens and your smaller code corpus with 1,000 high quality tokens. or sorry, 10,000 documents and 1,000 high quality documents or something like this. Now you're kind of like normalizing over the number of tokens in the output. Yeah. So papers often also report negative log likelihood, lower being better because this is what's used in the loss function of the models. So this is also, something to pay attention to. Did I see a hand or? Okay, cool. So one thing to be careful here is, let's say you want to compare Llama to GPT-4. Llama uses the Llama tokenizer. GPT-4 uses the GPT-4 tokenizer. If that's the case, actually the denominator here could be different between the two models. And if the denominator here is different between the two models, I can train a really, really good character-based model that predicts characters because there aren't very many characters. And if I divided by the number of characters, that'd be really unfair to the token-based model because I'd be dividing by a very large number of characters compared to a very small number of tokens. So just if you're comparing two models, be careful that you're dividing by the same denominator here. Otherwise, it might be a problem. Cool. Next, I would like to talk about per word cross entropy. This is basically the same as per word log likelihood. The only difference is this is minus. So we're doing, and actually, sorry, that minus should be out in front here. It's not this minus this. It's the negative log here. The other thing is we typically take the log 2. And the reason why we take the log 2 is, sorry, I skipped the quiz, but the reason why we take log 2 is there's a very specific connection between probability and information theory and compression. And any probabilistic model can be used to compress data. And basically what the entropy is this is a lower bound on the number of bits that you would need in order to compress data using this probabilistic model. So let's say I created a really, really good language model, and then I wanted to use it to create a really compact zip file of Wikipedia. I would be able to do that. And the smallest possible size that Wikipedia could become would be this log entropy times the number of tokens in Wikipedia, or this entropy times the number of tokens in Wikipedia. And so the way this works, I think maybe some people have taken an information theory class and learned about like Huffman coding or other things like this. But the basic idea is if the output is more likely, you'll use a shorter output, shorter bit string to express it. So for example, the word the, you might use a bit string of 01. But Carnegie or something like that, which is a very infrequent thing on the entire internet, you might use like a much longer bit string like this, just because it doesn't happen very frequently. So you wouldn't want to, you can use more bits to express it. And I'm not going to go into lots of detail just in the interest of time here, but if you're interested in this connection, I would encourage you to take a look at arithmetic coding. It's a beautiful algorithm. Basically, what it allows you to do is it allows you to encode a stream of data by gradually subsegmenting a probability space. And so just to give a quick example here, let's say we have 3 tokens, and our prediction for the first token is 50% and 33% and like 17%. And then the first token is actually this token number 2. We then subsegment the space and gradually find a bit string that is just large enough to express the space that that is subsegmented according to these probabilities. So basically, if the space is larger, we can find a shorter bit string that fits within this the space. But if the space is smaller, we need a really long bit string before we can find a bit string that corresponds to that segment of the space. So this can be applied to any language model, and this gets very, very close to this entropy estimate here when you're compressing an output. Which also means that if you get a really, really good language model, you could also compress the entire internet into like a much smaller disk than you would if you did other compression algorithms. Cool. So yeah, sorry. Yeah, go ahead. So are language models generating new content, or are they compressing and decompressing content? Most of the time they're generating new content, or at the very least, they're generating things from their parameters, which might be new, or it might be somewhere in their training data. They can be used for compression. So this is like a possible use case for language models, but most of the time, no. This is lossless. So this if you use this algorithm, it is a lossless compression method, but don't mistake this with like language models taking training data and like quote unquote compressing them into their parameters. That's actually something different than what's going on here. So you could search for arithmetic coding. You can search for arithmetic coding language model to see examples of applications of this. This is very different than taking information on the internet and encoding it in the parameters of the language model, which is another thing that people talk about when they talk about compression. Cool. So next is Perplexity. This is another thing that you hear quite frequently. Perplexity, basically the way it works is you do e to the negative word log likelihood or 2 to the entropy. And basically this is an exponentiated version of the previous metrics that I talked about, but it has a very intuitive interpretation. And so if I have this sentence here, and I say, when a dog sees a squirrel, it will usually, does anyone have an idea what might come after this? Chase, bark, run. Yeah, these are pretty good ones. So here's an example of calculating this according to a language model. There's also lots of other things that nobody guessed, like be or jump or start or run or try. But the basic idea behind Perplexity is it's kind of the average number of guesses you would need to take before, if you randomly selected from a language model's probability distribution, before you got the correct answer. And so if the next word was B, you would basically, for this particular token, you would get a perplexity of 28.4 because you would need to sample from the language model an average of 28.4 times before you got this token. And so for easy tasks, your perplexity might be like 1.5 or 2. Like for binary classification tasks, you would hope it would be pretty low, for example, because you would hope you'd get the correct answer more often than not. For things like freeform generation, it might be a lot higher, like 7 or 8 or 20 or something like that. Okay, so I talked about n-gram language models. The next thing I'd want to talk about is language models where we actually learn the parameters. These are, the first one is featureized log linear models, very similar to bag of words models that I talked about before. Actually, the first person to do these was Roni Rosenfeld, who's the head of was the head of the machine learning department until recently here. So if you want to go back and read some of his old papers, you can find it. Yeah.
I did have a question about perplexity.
Yeah.
Since it's exponential, how hard is it to calibrate and understand what the loss is sort of like? Because it can be really
Yep.
small and really.
Yeah, so for perplexity, basically, how do you know if it's good or bad? It really depends on what you're measuring the perplexity of. For like general purpose text, I could give you a rule of thumb that it'll be between like 3 and 20 or something like that generally. But the problem is like what kind of text are you trying to model will play a big role in that. So like I think the strongest models just on general web text get down to like 4 to 8 or something like that. But yeah. If you're modeling something that was not profuse in the training data or out of distribution, it'll go much, much higher than that.
Is this just normalized likelihood? Like if you exponent negative log.
This is exponentiated per token likelihood, yeah. Exponentiated per token negative likelihood. Yeah. Cool. So next, so featurized models basically calculate the features of the context, and based on the features, calculate probabilities, optimize the feature weights using gradient descent. So here's an example. We would look up the features of giving in a position 2 points previous, and the features of A in a position 1 point previous, add a bias, add them all together, calculate scores, turn them into probabilities. So looks very similar to your bag of words model last time, right? And essentially, it's pretty similar to a bag of words model. And we optimize the features in the same way. There's one small difference that I made here from a bag of words model. Can anyone spot where it is?
Features are not one hot vector.
Features are not one hot vectors. Yes, that's kind of true. You're right with respect to the figure. In reality, you could kind of view this lookup as multiplying a one hot vector, as I mentioned last time. So it is still kind of one hot vectors. The big difference here is a bag of words model is position independent, and then this is looking up things according to their position. So this is looking up A in the immediately previous position and giving in 2 positions previous. So this is really, really important because giving A blank gives you very different probabilities than A giving blank, right? So you need to keep track of the previous position. Yeah. How different is it conceptually from a bigram model? Great question. I'm going to talk about that in a second. So if we look at the words we're predicting and the previous words we're giving A, first we look at how likely are the next words overall. So this is our bias, and this actually would correspond to the unigram probability pretty strongly as well. Like if something has high unigram probability, we'd expect it to have a high bias. The next thing is how likely are they given the previous word is A? And so when the previous word was A, it's very unlikely to get A again. Like suddenly A, despite the fact that it's likely in general, it becomes much less likely overall. So we would have a strong negative here. And similarly for the. And then for giving, this might have a smaller effect because it's farther away. It's maybe more indirect, but we're more likely to start seeing things like talk and gift and other things like that. That gives us a total score. And then we turn that into a probability and calculate a log loss. And sorry, the way we calculate the probability here, I just realized I actually haven't covered this yet, but we use something called the softmax. It's very similar to the sigmoid in that we are converting arbitrary inputs into a probability distribution, but basically it's E of the score for I divided by the sum of E of the score for all of the words in the vocabulary. So that's a softmax. And I think probably a lot of people are familiar with this. And so this takes arbitrary floats and converts them into probabilities. So then we take the log of the actual next token and do backprop. So there was a question about how this relates to the bigram model. It's pretty similar to the bigram model in some ways and pretty different in other ways. So it is not able to solve the problem of sharing strength among similar words because we're still using a discrete one-to-one feature between all of the previous words. So we're not able to share between, like, for example, bicycle and car. We are able to condition on context with intervening words. So for example, we would have doctor and then Smith, and we could learn to upweight the probability of doctor being 2 words ago, improving the probability of Smith 2 words later. And we still can't handle long-term dependencies. A problem with this model, one problem with this model is it's not able to learn combination features. So like a bigram model can learn Dr. Jane or something like that. And does anyone know a famous Dr. Jane? Goodall, yeah, exactly. That's the only one I could think of as well. But like Jane Goodall was a person who, there's probably a lot more, but that's the first one I thought of. It was, a famous person who worked with primates. Yeah, I was trying to think of what primate, but chimpanzees. Yeah. So anyway, so Dr. Jane is a combination feature. We wouldn't be able to capture that because essentially we have the probability change given Dr. and then the probability change given Jane, but we don't have the probability change given Dr. Jane, for example. So the way we fix this problem with combination features is the way we fixed problems with other features before. And there's something called feed-forward neural language models. So we fast forward 7 years from Roni Rosenfeld in 1996 to Yoshua Bengio in 2003. And the way this works is we create a feed-forward network. And the way it works is we look up 2 vectors here. We concatenate them together, and we run them through nonlinearities to calculate features, and we might run them through several layers of nonlinearities. And this gives us a feature vector, just like we had the feature vector for the neural networks from last class. And so now this allows us to capture things like Dr. Jane, for example. And here's some other examples of combination features. So we have word embeddings or token embeddings for each of the previous tokens. Feature 1 might indicate verbs. Feature 2 might indicate determiners like the and And then we have a row in the weight matrix. Together with the bias, it can capture a particular combination of the features. So for example, one row in the weight matrix might look at feature 1 in the second to previous word and feature 2 in the previous word and say, we want to create a combination feature that is only true if we have a determiner as the previous word and a verb in the second to previous word. So that would be like giving a blank or running the blank or something like this. So these could be very similar contexts. It can capture word similarity across them. It can capture combination features and other things like that. So that gives us a much richer way of modeling language. So if we look at where, and like one of the reasons why neural networks are effective here is they allow us to share information across training examples. So if we look at all the places where information is shared across training examples here, first, it's shared in word embeddings. So if we have similar words, the similar words can be given similar embeddings, which will allow us to share information across training examples with similar input words. We can also share probability across similar output words. So we have this matrix here that we use in calculating the final probability of the output. And so if we have similar contexts, we can basically give higher probability to words that appear in similar contexts. And that's because similar contexts will get similar hidden states. So like, for example, in a neural network, feed-forward neural network-based language model, we can say giving, throwing the, handling, all of those are similar contexts. So that will give a similar probability to the outputs. So does this make sense? Like, this is similar to what we talked about last time, but it's in the context of language modeling. Any questions or clarifications? Okay, cool. So I'd like to move on to a trick that we can do here. And one of the problems with language models is if we have a very large vocabulary, they can have very large embeddings. And so one thing that people sometimes, but not always do, is tie input and output embeddings. And the way this works is we can realize that when we look up embeddings, we're basically taking a single row from the input embedding matrix. And so this input embedding matrix can be input embedding size by vocabulary size. And the output embedding matrix is also a matrix that we multiply by the output embedding. And we get a vector the size of the vocabulary, so we can calculate the probabilities of the outputs. So if we set the input size and the output size to be the same, then we can actually use the same matrix for both of these. We can use the same matrix for the input and for the output. And this is called tying embeddings. And this is used, as I said, in some models, but not all models. This can reduce parameters, make them easy to learn, but it also reduces your flexibility somewhat because you can't use different embeddings when you have them in the input and output. Cool. So feed-forward neural network models allow you to share strength among similar words in context, can condition on intervening words, but they cannot handle long-distance dependencies. So now I'd like to talk about some models that can handle whole sequences. And the first, there's three major types of models. I'm not going to handle all of them today. But the first one is recurrent models. And the way these work is they condition representations on encoding of the history. And so, for example, we might have a recurrent neural network, and it takes an input, it calculates a hidden state. Then we have another example of the same network, and it feeds in the previous state and calculates the next state. And we have this essentially recurrent function that calculates the next state over and over and over again. The next one is convolution. And the way this works is we essentially calculate the state based on only the immediate neighborhood of the previous ones. And so if we have a convolution with a total window size of 3, we step through and we calculate each of the representations based on a size 3 window. And attention, we condition representations on a weighted average of all tokens within the window that we're considering. And so basically, if we have full attention over the entire sequence, we would calculate based on a weighted average of the tokens. So for recurrent neural networks, these were created a long time ago, I guess 34 years ago, and they're tools to remember information. If we look at a feed-forward neural network, the basic way this works is a feed-forward neural network takes some information that you looked up, it transforms it, it makes calculates hidden representations, it makes a prediction. A recurrent neural network does the same thing, except it uses the previous hidden states to make a calculation. And in math, basically, this is like doing a linear transform, but instead of doing a linear transform over only the input features, we also add the hidden features when we make this calculation. So if we unroll this in time and look what processing a whole sequence looks like, we start out with some vector. This could be like a 0 vector, it could be a randomly initialized vector or a learned vector. And we run it through this calculation and make predictions. One important thing to note is that, and then when we train the model, we basically calculate the loss based on the true labels and sum them together and get a total loss. So the important thing to know about recurrent models like this is the unrolled graph is a well-formed directed acyclic graph. So if we look at this graph here, there are no cycles in this graph, right? And because there's no cycles in this graph, if you remember what I talked about last time, a backpropagation can be used to optimize any parameters in a graph that doesn't have any cycles in it. And so because there's no cycles in this unrolled graph, we can just optimize it using normal backpropagation. And so we have the sum here, and we can just backprop into all of the previous time steps. And another important thing is parameters are tied across time. And so this RNN, if we go back and look at what the RNN looked like, this was a function with some parameters WH and WX, but these are applied at every time step. So we're using the same WH and WX for time step number 1 and time step number 2, time step number 3, time step number 4. And this is important because basically the recurrent neural network can learn from every time step. We're backpropping into the neural network at every time step. This is also a super, super important feature of all sequence models in general. And the reason why is because we don't want to learn like a different network for sequences of size like 21, like a completely different network for sequences of size 21 and 22 and 23 and 24. We want to have something that basically shares the parameters regardless of the sequence length. And so RNNs are one example of this, so are convolution and attention. And I'll talk about the other two soon. Historically, this has been called backpropagation through time because you're just backpropping through an unrolled sequence in time. And yeah, this is where the parameters are shared. Any questions about this? One thing I should point out is that we don't use recurrent neural networks directly very often, but we use a lot of the concepts from recurrent neural networks in some of our kind of more advanced models. So I'll talk about those a bit more when we get to the transformers lecture next time, and I'll refer back to recurrent neural networks and make contrasts with them. There's another thing called bidirectional RNNs. This is relatively simple. The basic idea is that you run an RNN forward and an RNN backward, and you calculate the representations from both, and then you concatenate them together and feed them into the next layer. So this is not good for language modeling because language modeling, as I said, you need to make predictions based only on the previous thing, but it is good for encoding sequences if you want to get representations from sequences. And we do something similar in attention-based models, which I'm going to talk about next time, because attention-based models also sometimes we want to calculate bidirectionally and use information from the past and the future. So when we're training neural networks in general, we have a really big problem called vanishing gradients. This is something you need to be very careful about because it will kill neural network training and cause lots of problems if you make a mistake here. It's particularly big in RNNs, but it's also a problem in other models if you're not careful. So the basic idea here is that gradients decrease as they go through multiple nonlinear transformations. And just to give an example, they decrease or they increase systematically. And so the opposite example is exploding gradients, but that's a little bit easier to handle than vanishing gradients. Just to give an example, like let's say we had a nonlinearity, and we used a nonlinearity called the tan H nonlinearity, which looks like this. If we take this tan H nonlinearity and we look at its gradient looks like this, basically. So if the input through the function x is close to 0, you get a nice gradient that kind of pushes you in the direction of learning something. But if you get anything that's very far away from x, like let's say you get a value that's like -30 into this function, basically your gradient will go to 0 and you'll start losing gradient information in earlier layers of the network. And so because of this, like recurrent neural networks have a very big problem where if you go far away from where you calculated the loss function, you start losing information and they become very hard to learn. Another thing is you can have small or big weights in matrices. So like let's say all the weights in your matrix were like 0.001 or even worse, 0. Then if you have a matrix with 0 weight and no bias, then that will also kill your gradient and your gradient will disappear. So there's lots of ways to get your gradients to disappear. There's only one way to get your gradients to not disappear. The one way to get your gradients to not disappear is to not make any modifications to the inputs and outputs. So the only function that doesn't change gradients is the identity function that keeps the input and output exactly the same. So there's a method that causes this, or that allows this to happen. And it's implemented in this model called the LSTM. The LSTM is basically a method that has an additive connection between the previous state and the next state. This is called a memory cell. And this additive connection basically ensures that gradients will not disappear. There's another thing like this that's used in all transformer models. It's called residual connections. They both have basically the same idea, but I'll talk about residual connections next time. So I don't think I have time to cover convolution. I'll do that in the next class, but it's very simple. So thanks, everybody. I think we're out of time, so I will take any questions up here.